analyzing that graph, it gives us helpful information about the behavior of the function. Remember in elementary calculus, we used to graph a function to understand its maximum, its minimum, the behavior of the function locally and eventually globally. We have the same interest in function in two or more free variables. Note that for function in two variables, it's much more easier to visualize them, but for adding more variables, we get difficulty visualizing those functions because we get to a higher dimension. So definition of the graph of a function. So first of all, recall that in two-dimension graph of function y equals to f of x is the collection of all points that satisfy the relation between y and x. It is the set of all x and y's such that y is equal to f of x. This is part of the plane. In 3D, instead of having two ordered pairs, we're going to have three ordered pairs. In 3D graph of function like z equals to f of x and y is defined as the set of all x, y, and z values such that z is equal to f of x and y. That's how we define the graph of the function. In two-dimensional, it's part of the plane. In three-dimensional, it's part of the space. So here you have your space, x, y, and z, and you get some graphs. Suppose you have this graph here. And in 2D, you have a graph like this. This is the graph of your function. That's it. One of the famous methods analyzing the graph of function in two free variables is trying to slice this graph, slice this object, and analyze that using level curves. So to analyze a function like z equals to f of x and y, we can slice the graph using z equals to a fixed number like k, just a number. And graph what we call the level curves. So for example, suppose you have this graph, this 3D object, whatever it is, you start slicing this with planes z equals to k. Remember that when you're talking about z equals to a fixed number, these are all parallel planes. z equals to k, a fixed number, you get a slice of the whole object, which in this case is similar to something elliptical maybe, circular maybe. Then you slice this by another plane, z equals to L, for example. Another fixed number. And then you get another level curve, which is might be elliptical, might be circular, depending on the definition of function, z equals to f of x and y. And we start analyzing these level curves. Very well. For example, if you have this object, 3D object, f of x and y equals to negative x squared minus 2y squared, you can slice this by using different level curves, different z equals to k. You see this plane, which has equation z equals to k, is moving along, slicing along this 3D object, and you can see these level curves in 2 dimensions on the right hand side. Level curves, intersection between the plane and the 3D object. These are all intersections. From top, you get the smallest circle. It gets larger and larger and larger. And as you can see, as we go along, the intersections are becoming just some curves. By analyzing these circles on the right-hand side, we can analyze this 3D object. Well, let's take a look at one example to feel more comfortable about the level curves. Example. This example says, well, sketch the level curves of the level curves of, what do we have? We have f of x and y, which is equal to 6 minus 3x minus 2y. For here, our k values are given to us. One k is negative 6, the other one is 0, 6, and 12. Okay, very well. We have an object in the space. Instead of graphing this object in the space, we are interested in analyzing its level curves. So this guy is in 3D. Whatever this object is, it is in 3D. We're going to analyze this in 2D by finding its level curves. Our goal is to analyze this object in 2D using the level curves. Okay, the very first k is minus 6. So remember that we said z equals to k. Our z is equal to negative 6, and z also is equal to f of x and y. What's the meaning of that? It means that we have to take this linear combination and set it equals to -6 and solve it. So 6 minus 3x minus 2y is equal to -6. What's the meaning of that? It means that I have 3x plus 2y equals to 12. In 2D is the line. Next k. Next k is equal to 0. What's the meaning of that? It means that I'm dealing with plane z equal to 0 or xy plane. So my z is equal to f of x and y. What's the meaning of that? It means that this quantity is equal to 0. So 6 minus 3x minus 2y is equal to 0, or 3x plus 2y is equal to 6. Another line parallel to this line. And we can continue this process. The next k is equal to +6. So z is equal to 6. It means that your quantity is equal to 6. 6 minus 3x. 6 minus 3x minus 2y is equal to k, which is 6. You can cancel out 6 and 6. 3x plus 2y is equal to 0. Another line. Continue this process and then graph these lines. In xy plane, look at these lines. Okay, this guy has a negative, suppose it's a negative slope. X plus 2y is 0. Is equal to 6. 3. And 2. Okay. These lines are parallel to each other.
Hey, Professor, the video just froze.
So our next line, 3x plus 2y equal to 6, and the rest of these lines, and just continue graphing the rest of them. These are all part of your level pairs of this object. So let us take a look at our graph. Z is equal to 6 minus 3x minus 2y. As you can see here, you have a plane in the space, and you start slicing that by different graphs. Trying to see if you can find a nice function. Okay, maybe this guy here is better. Okay, I need a 2D function. It doesn't seem like to have it. Maybe this guy. Okay. Not f of x. Look to have, let's see, y equals to 6 minus 3/2 1/4 x. Okay, let's see if it's graphing this here. has the same color. You can see that. That's fine. Now I'm supposed to ask you to sketch the level curves of the following function. And I'm not going to give you any k. How do we analyze level curves if we don't have k values? If we don't have those parallel planes? So here we have g of x and y equals to square root of 9 minus x squared minus y squared. We don't have any k values. We don't know what z equals to k is. So in this case, we have to fix z equals to k and start solving the equation. So since z equals to k is not given, we solve a general equation. Solve a general equation. What's the meaning of that? So we know that z is equal to g of x and y, and z is equal to k. Well, it means that we have the square root of 9 minus x squared minus y squared equals to k. But what is this equation? First of all, note that inside the radical, you have a quantity. It means that this quantity must be greater than equal to 0. So 9 minus x squared minus y squared must be greater than equal to 0, because this quantity is inside the radical. What's the meaning of that? It means that x squared plus y squared is less than equals to 9. What's the meaning of that? It means that you have inner circles. Inside a circle, you have a shade. These are all points inside a circle. So you're actually forming a disk. So keep that in mind. Well, okay, now if I raise both sides to the second power, I get 9 minus x squared minus y squared equals to k squared. This guy is just a number. Okay, well, now I have x squared plus y squared equals to 9 minus k squared. What do I have? I have x squared plus y squared equals to r squared, the radius squared. So this guy is equal to r squared. It means that the radius is equal to square root of 9 minus k squared. What's the meaning of that? The quantity inside the radical cannot be negative. 9 minus k squared must be greater than equal to 0, or k squared is less than equals to 9, or k is bounded between -3 and +3. So what are the level curves? The level curves are circles, concentric circles with a radius r equals to square root of 9 minus k squared. We found the domain. So the level curves are circles with center 0 and 0 and radius equals to square root of 9 minus k squared. You can easily just graph this. If k is equal to 0, you get 3, the largest circle. And when k is exactly equals to 3, -3, you get the origin. And the rest of these circles are concentric circles. Not a beautiful circle, but still we get the level curves. Level curves in map making. As you can see here, we have, for example, some mountains, and they cut the mountains by z equals to different k values based on the height of the mountain. The k values are going to be different. And as you can see, the level curves are in 2D. For example, take a look at this small piece here. When you slice this small piece by z equals to a number, you get your level curves, which is this shape down here. So the intersection between the plane and this piece of the mountain is going to be this small shape here.